Hello.
Hello, sir.
Hello,
Yeah,
sir.
Good evening.
Yeah, good afternoon. So, should we start? I don't know whether more people are joining or not.
So they must be.
They was joining. Okay. So before I start, I mean, so tell me any questions that has been on things that was done till now.
Sir, in the assignment that we have to submit day after,
Hmm.
there is a mention of an algorithm that I don't think we've studied, which is the Kruskal's algorithm. Are we supposed to figure that out on our own, like from the net?
Okay, so there is a Kruskal's algorithm. So if yeah, so maybe that's one thing you can do. Or okay, so if it's a Kruskal's algorithm, it's fine if you skip it also. Let me just see.
It's mentioned in the last question.
Right. Actually, this Kruskal's algorithm, we have kind of done it. Okay, so it was done in the sense that I believe this was something that was done in the class right after the mid-sem, where the main idea is that you keep on picking up the weakest, the edge with the smallest. So you sort the edges and keep on picking up the smallest edge. Okay. If it doesn't form a cycle among the set of things that have been selected. Now, so in case you have not followed it, I think you can just take a look at the algorithm that is there in the internet or in the books or something. The proof is something very similar to what was done, or something that was done in the class or the right after the mid-sem. So the crucial fact is that any MST, okay, so not any MST, but there exists an MST which contains the lowest weight edge in the graph. So do you remember this particular thing that was done? I think Manasvi did it, I think, if I'm not wrong.
Yes, sir.
Yeah, so you guys just take a look at this algorithm from the book, and you should be able to do that that problem also. It's not a big deal. Yeah. Okay. Any other questions, doubts? Okay, so if not, so let me start with today's class. So it will be kind of a shortish class, I must say, because I know that this is a long day for you guys. So the thing that where we were till now. So we have defined this concept of the class, the polynomial, the class what we call P, the polynomial time algorithms, and we have also introduced the class NP, non-deterministic polynomial time algorithm. So this is the set of all problems that you can that can be solved in polytime, and these are the set of all problems for which the yes answers, or the answers in which the function value is 1, or the one answers, whatever you want to call it. Okay, the one answers has a poly size witness that can be verified using a polytime algorithm. Is this fine? Hello.
Yes, sir, this is fine.
Okay, good. So, and what all things we see? We saw that, okay, there is this P, which is a subset of NP. And we kind of called off these two things about, we drew this whole thing. So there is this class of NP and there is this class of co-NP. So co-NP is nothing but the same definition as NP, except the one set here becomes 0. Okay, so 1 is 0. So it's a 0 in there. And we have this, use this, we have a small set here, which is P. Now P is contained inside NP. Now, so yeah, so another thing that we kind of tried to answer, that there are lots and lots of important questions that are in NP, and we don't know whether they're in P or not. Okay, and so there are problems over here and everywhere basically. So problems that are in NP, but again, I'm not saying that they are not in P, but we don't know whether they're in P. The reason is that whether P is equal to NP or not, this is a big question.
NP equals to co-NP.
No. So we know, so even whether NP equals to co-NP or not, that is also a big question. Okay, so if NP is equals to co-NP, then certain things happen. So I mean, there are lots of things that are known. It might very well happen that so what all things we know? So what we know is that if actually P becomes equals to NP, then NP is equals to co-NP. Okay. But not the opposite direction. Not necessarily the opposite direction. We don't know our proof of that. Okay, so there are a lot of things that we know otherwise, and in fact, just like I have defined you NP and co-NP, you should not think that all of this, these are all this that is there in this in the world of problems. Okay, so there are problems which are beyond NP, beyond co-NP, and so on. In fact, one important thing is that, so these are all this set. What is NP? NP are all the set of problems that are in NP. No, sorry, that is that which have a poly-sized witness and a polytime algorithm. Now, can you, but this is not saying that what is the time complexity of solving it. So can you design an algorithm for these problems? So if I give you a problem in NP and I tell you that, okay, please design an algorithm for this problem, can you design it? And if so, how much, what will be the runtime of that algorithm?
So could you please repeat?
So I'm asking that, so NP, can you say that, can you design if I ask you design an algorithm for NP problems, for problems in NP, how will you do it?
So we take this set of possible solutions and check each of them if it is correct.
Excellent. So because, see, a problem is in NP, that means the yes instance has to have a small witness, right? And that small witness can be checked in poly-size. So what happens if I just go ahead and check out all possible this poly-size witnesses, all possible poly-size candidates? Okay, I can say, okay, is this a candidate? Is there a candidate? I look at all the possible. So this polysize is a fixed polysize, right? It's a bounded by some polynomial. So I want to go and check all possible possible witnesses, and I want to verify whether those witnesses are either valid witness or not, right? Now, so what should I do? So an algorithm will be, okay, for all witnesses or possible, or for all witnesses x, sorry, not x, I use y, of size less than that p of x, right? Check if that function, if you remember this thing, equals to 1 or not. So remember that NP was defined as that thing, right? NP was defined with that particular polynomial. So if for input x there is a witness y, such that something happens.
So, but then how are we fixing P? Is because
No.
we are just given a problem. Then how do I identify that polynomial?
Yeah, so we don't know the problem, but there exists a problem P, right? So look at it. So L is in NP. Well, what is the L is in NP? Right? So L is in NP meaning, okay, what does it mean?
So that means that exists a polynomial such that
There exists a polynomial, right?
right.
And there exists an algorithm A. Okay, this is a polytime, such that for all x, for all x, for all x in f inverse of 1, there exists an y, which is also polysize. Polysize meaning, I should write it here, size of y is less than p of size of x, and ax actually should be, yeah, ax y is equals to 1. It is if and only, in the sense that, and I mean, and for all x in not in 0, you cannot prove that. So this is if and only if x is in, no, if and only if f of x equals to 1. Right. Now, so that means if I give you a problem, there exists a problem P. Okay, I don't know the P possibly to start with, but if I have been given a problem, then I can, by the definition of this thing, there must be a fixed polynomial P. Right? And you can do this thing.
So, but this none could be infinite, right?
Which could be infinite? Which one
sorry,
can,
sir? So this whole algorithm could be infinite time, right? Because
is it?
since we
Yeah.
so well we know that exists a polynomial, but then
No. See, but when I say you give an L, there is a polynomial meaning I have given you an L, so that means you know a P. So this is exactly that P that you put it here.
so how do we determine a P from an L?
Okay, so I am not saying that you are determining the P from the L, but there exists a polynomial. Okay, now whether you will be able to find a polynomial algorithm or not, that's a different issue. Okay, but there exists a polynomial.
So, but then this clause that you've written, if this were a proper algorithm,
Yes.
then we would need to provide this algorithm with a
Yes,
deterministic P,
you have to give a deterministic P, which exists. You might not know it. You have to know it by, so for a particular language, there exists a P. I mean,
so right.
So if I give you vertex cover, you know, oh, okay, so that means the P should be less than n. Okay, let me do this one with n. a p should be, or a p of x is just a one, say x square or x or something like that. Okay, so for a language there exists a p. So that means if I know this p, or if I can somehow find that p, so there exists a p which is the polynomial for which this algorithm will work. Or let me put it this way: there exists a p, there exists a polynomial p such that the above algorithm, this algorithm, gives the correct answer.
Oh, okay, right. So maybe from the question we will have to derive some result on what could be a bounding polynomial, right? So
Something like
as
that,
you're
yeah.
saying that for a vertex cover, all the information is captured in linear order
Right,
polynomials as well.
right.
Okay.
Okay. So it means that if I give you a problem in NP, it doesn't mean that it doesn't have an algorithm. It of course has an algorithm. Okay. But what is the runtime of this algorithm? Can you tell me what is the runtime of this algorithm?
Solution size
Exponential.
solution to the power of polynomial.
Yes. So how many are there? So there are all possible strings of size p of x. This one is a polynomial check, right? But the total, the for loop has to go over all possible witnesses of polynomial size, right? Right. So how many y's are there such that size of y is less than p of x? This is actually equal to 2 to the power p of x.
Yes, sir.
Right. So that means this algorithm runs for 2 to the power p of x time, right? So which means that this gives us a exponential. So this is an exponential, right? So that means L has an exponential time algorithm. Now, see, this is where things are interesting. It is like an existential result. Okay. As soon as you prove that an algorithm, a problem is in NP, you know that it has an exponential time algorithm. Now, that is an existential result. You might want to find an algorithm. Okay. Now you go and find it. So that's a constructive algorithm. Okay. So just like I had defined P, so what was P? So P is the set of all problems that are solvable in polytime, right? Or that means which has a polytime algorithm to solve it, right? Similarly, we can define this function called exp. This is the problem that are solvable in exponential time. Now, what is exponential time meaning? So exponential time meaning time less than or equal to 2 to the power order p of size of the input, where p is some polynomial. So what we have therefore is that the p is less than is contained inside NP. So all the problems that are in P, of course, are in NP, and all the problems that are in NP are in EXP. Okay, so that means it is not that the problems that we are talking about in NP don't have an solution. It does have a solution, except that the most canonical solution that we can think of are exponential times. So for example, if I give you the vertex cover problem and ask you, is there a vertex cover of size less than R? What will you do? You can go and look at all possible subsets of the vertices of size less than R, right? So that is n choose R. So which is basically something of the order of n to the power R, right? So you can look at all possible subsets and check whether any of those subsets forms a proper vertex cover or not. And that's it. Yeah.
Yes, sir.
Okay. Clear? So this is important, very important, that this is actually, you should not have this feeling that this is the end of it. Okay. So this is where I think complexity things comes in. So you have this P, you have this NP, on top of it, you have the EXP. In fact, you can keep on putting round and round circles here. Okay, there's a double EXP. Okay. And you can continuously do it until you hit this class of the maximum class that you can think of. And this is something that I kind of talked about in the last class. Oh, I forgot to put the link in the web page for this. But this is the final class you can think of. These are called the set of all decidable languages. Decidable languages or computable languages, whatever it changes with the. So these are all the set of all problems that can be solved by someone or sometime, infinite amount of time. Okay, so for which there is an algorithm that halts and finds the solution. So now, if you say, what are those classes? So this is this set of all languages that are defined by what I kind of talked about by Turing machines. Okay, so things that can be solved by Turing machines, and this is a set of problem languages that Hilbert was after to understand what is. And in some sense, what you can think of Gödel's incompleteness problem is that there exist problems that are beyond this set of decidable problems also. And there are problems that are not decidable.
Sir, what do you mean by the not decidable?
So there are problems which you don't know. I mean, there is no algorithm that can ever compute, output the right answer, even if it is runs for any amount of finite amount of time.
Can you give us any example?
Yeah, I'm giving you an example. Is proving is very hard, or proving it is equals to understanding of the Turing machines and all. And so, so one example is basically what is called the halting problem. Okay, so I give you a program and I go and tell you that go and check whether this program halts or not.
Sorry, sir. The program what?
Halts.
Okay. Halts means stops, right?
Halts means stops. Yeah.
Okay.
Okay. Now, actually speaking, halting. So this is something very interesting because there is a lots of, just like in the case of numbers, right? You have the infinite class of numbers, like sets, this set of numbers which are size infinity, like the integers and rationals and reals and all. But inside that, there's a hierarchy. The number of integers is equal to the number of natural numbers, is equal to the number of rational numbers. But the number of reals is more than the number of rational numbers. Now, I hope that you guys have seen such things, right? The diagonalization techniques of Cantor, yes, and all those things.
Yes.
So similarly here, there are hierarchy here also in this area, meaning in the area outside decidable problems, there is also a hierarchy of which is more undecidable than others. Okay. It is way beyond the scope of this lecture, so I don't want to go into that one. But again, just to give you this thing, this is the whole area called computability theory. The theory that deals with exactly this set of all languages that are not decidable, how much undecidable they are.
So
Now,
does these, I mean, do these things appear in real life by any chance? These kind of computability problems.
I mean, real life in the sense of that many of these techniques have been used to prove mathematics results in number theory. For example, lots of big number results on number theory has been proved using this whole thing. Okay, so it's a huge. I mean, it's a, you can think of it as a part of a logic kind of stuff. So it's not, in some sense, it doesn't have an application as such you can think of, but they have this gives you a different set of techniques that are used in various other topics and work and all. So I don't want to go into this computability theory at all, because this is a bit of a, I mean, just like in the case of set theory, right? You have this whole set theory business which deals with how large are this LF naughts and LF ones and so on and so forth, right? Computability theory also goes in that genre. But you can ask the other question, right? If I give you a problem here, a problem that is decidable, and I ask you how much, I mean, how quickly can you solve it, and so on and so forth, right? Or what are the hierarchy within this set of all decidable languages? So this area is what we call as complexity theory. Surprisingly enough, I mean, which is something that even puzzles me to this day, that is the computability theory, although it is kind of starts from the work of Turing and Gödel and all in the 1920s or something, and till now it's a very strong subject that keeps on going in the logic community. The world of complexity theory surprisingly is much younger. It started only in the 1960s or something. But now it's a big thing, particularly with the world of computers coming in and all those things. So we are more interested in designing algorithms, understanding the limitations of our algorithms, how hard is a problem, and so on and so forth. And many of them are very, very, very crucial. I mean, for example, all your cryptographic understandings, cryptographic protocols, the one that you use to do the Zoom meeting. Just one second. Hello, can you hear me?
Yes, sir.
Yeah.
Yes.
Yeah. So, that's what I was saying. So this whole cryptographic protocols that happens, okay, they are usually the security. What is the main idea of the cryptographic protocol? That you are trying to send a message to me in such a way that even if somebody else are going to read that message, they will not be understand what you are sending. Now, this is not some kind of a war and games and all those things. I mean, it is of course used in such things also, but it is as simple as our Zoom call. The idea is that the Zoom call is being passed through the Wi-Fi or the whatever internet lines and so on and so forth. So anybody can tap into it. But so we want to be secure. That means even if somebody taps into it, they should not be able to understand. Or more importantly, your credit card, right? That you are sending you're doing some transactions online. Everything is going through the internet. Even if somebody taps into it, they should not be able to still kind of mimic you and kind of get all your information out. So that is cryptography for you. Okay, now how is it done? Actually, almost all the cryptographic protocols are based on some problem which we call one-way functions, functions which are hard to do. For
Sorry,
example,
sir? Functions which are hard to what?
hard to solve. Okay, for example, if I give you a number and ask you to go and factorize that number, or can you give me a, so I give you two numbers, say, I give you two primes, P and Q, sorry. And I give you two primes, P and Q are primes. And I ask you what is P times Q. Will you be able to do it?
Yes,
Yes, sir.
Yes, sir.
How much time will it take?
what I want.
Log P plus log Q or something like that.
Something like that, right? It's just a matter of you have a simple algorithm for that. Easy. But what happens if I, instead of that, I give you P times Q? I don't tell you what is P, what is Q, and give you P times Q and tell you factorize it. Will you be able to do it?
In exponential time.
It will be exponential time. Now you have an algorithm which is exponential time. That doesn't mean that there is no other algorithm that is exponential time. That is very simple. That is better. Okay. Now, surprisingly enough, many of the initial protocols, which are many of them are used till date, are based on this fact that multiplication is easy, factoring is hard. So if I think of the hard functions, okay, factoring is hard, and what is easy? Multiplication is easy, and even division is easy. So if you know P, you can know Q. But if you don't know either of them, then it is hard for you to do it. And that under that premise, the cryptographic protocols are made.
Are these terminology standard? I mean, easy, hard, these things?
Yeah, so kind of I will kind of motivate it a bit more just now. Okay. I mean, easy means you can think of easy means they are all can be done in polytime. And hard means they cannot be done in polytime, say. In polytime. Okay. So it is important for many times, it is important to understand how hard is this the function. And it's not just the cryptography, it has connections to so many other things. Okay. So to understand how a particular function, what is the actual complexity of a function in this set of all zoo of complexity classes. So these are called complexity classes. This P, NP, CoNP, X, EXP, and these are huge zoo. Okay. And not all of them are based on times. Some of them are based on something else, like space. Some of them are based on interactive message passings and so on. So basically, this hard, the concept of how hard is a function, that's the relative that depends upon what is the model of hardness we are talking about. Okay, so this is where we are. That okay, so there's this computability theory for things which are beyond decidable, and then there are complexity theory for the functions that are within the set of all decidable class. And we want to understand how hard is the subject. Okay. So now, is it fine till now?
Yes, sir.
Yes, sir.
So I will now go into a slightly big detour and talk about something else. Okay, that is very crucial to this whole concept of complexity theory. So we kind of talked about, say, like we told you about the set of all rationals is has the same cardinality as set of all integers. How do you do it? Right? You have a definition, right? you say that, okay, there's a one-to-one correspondence and so on and so forth. Similarly, we want to kind of understand how does two problems relate to each other. If I give you two problems, okay, the P1 and P2, I want to know which is hard, which is easy. I want to know, are they kind of equivalent? Okay, so this is where it's very important. This is what we call as reduction. So before we go into this formal definition of reductions, let me go into a different way of introducing it. So let me start with giving you 5 problems. Okay, so they are not decision problems, they are actually optimization problems, but that's fine. And I would like you guys to think about these problems. Okay, and see how can we try to come up with a common aspect out of it. Okay, so here is the first problem. Say, so
To come up with a
common way of solving it.
okay.
So here is the first problem. So basically, you have a company has 3 wagons. They want to fill up these wagons. Each wagon has a weight capacity and a space capacity, and there are some 4 different cargoes. Okay, and for each of the cargoes, they have a weightage and volume, and also there is a profit involved. And of course, the idea is that you want to take in each wagon as much cargo and as possible in such a way that in each wagon, the total weight capacity is not exceeded, the total space capacity is not exceeded, and the profit is maximized. So is this problem clear?
Sir, sorry, sir. Could you please repeat once again?
Yeah. So can you read this
Yes, sir.
problem?
Yes, sir. Okay.
Maybe that will give you more understanding.
Sir,
Yeah.
so ultimately we have to decide on how much of C1, C2, C3, C4 we want to like fill in.
In wagon 1, how many of
wagon.
C1, C2, C3, C4 you want to fill in wagon 2?
Okay.
How much? Okay.
So if we decide on those variables and set up equations.
Very good. You have already kind of hit the nail in the coffin to some level. Okay. Just hold your thought. I will come back to that.
Sir, so each wagon will be loaded with some amount of cargo, right?
Correct.
Okay, all right.
Okay. Okay, so this is one problem, right? So let me go into another problem. So here, okay, this is something that I possibly have discussed it earlier, but something say you have in a marketing company and you have overall a budget of 6 crore, okay, and you have only 10 people who are handling the advertisement. 6. You want to kind of spread it across. So you have these 2 upper bounds. 6 crore is the total budget and 10 people. Now for each of this, there are different things that you can do. You can either say that, okay, I will put advertisement in Cricket World Cup. The total cost will be 3.5 crore. And the amount of people you will be able to reach is 10 crore. But the total number of people that you have to invest or to have to kind of put in to handle this whole issue, whole thing is 5 people. Okay. The other option is that you can go for IPL, which is costlier, but also reaches out to many people. And the total people you need to work on is 7. And so on and so forth. Now, of course, you cannot say that I will just do half of IPL. No, such things are not allowed. You have to do whole of IPL or whole of Cricket World Cup and something similar to all of these things, right? Now, during this time, okay, so what can we do? Of course, you can say that, okay, see, maybe I can buy the Cricket World Cup for 3.5 crore I have 5 people. So now I am still left with 2.5 crore and another 5 people. Maybe I can try to do it in the TV ads of the peak hours. And then you say that, okay, in that case, I am done with 1.5 crore. So 3.5 and 1.5 is 5 crore done. The number of people required is 9, and that's it. So I am reaching out to say 14 crore people. Now, is there some other way of reaching out to more than 14 crore people? Because I am, after doing that, I have left with 1 crore. For this 1 crore, I have no way I can buy, of course, radio ads or TV ads and so on, but they will need more than 1 people, which is all that I am left with right now. Right. So maybe some other person says, okay, no, you can put your money in IPL. So it's 5.2 crore. And you reach out to 15 crore people and you spend 7. If I do that, I'm left with 0.8 crore and 3 people. So maybe I can think now, what can I do? Right. Maybe I can put money in the web ads or something. Right. So this is a kind of I mean, of course, there are toy examples, but the problems are kind of very much real issue. So is the problem clear?
Sir, here we might put indicator variables like for each of them, and then
very good.
Maybe.
So good that you guys are thinking that direction. Yes, again, hold your thought there. Okay, just 1 second. Hello. Yeah. Hello.
Yes.
Yeah.
Yes, sir.
So I have another one, say here. Okay. So this is a completely something different. So you have the MTech students are there, say S1 to SN in ISI, and there are the M faculties F1 to FN, and each student submits a list of faculties with whom he or she wants to do research, and each faculty submits a list of students whom he or she will be happy to supervise. Okay. And but each faculty must also submit a maximum number of people he or she would be willing to submit. Will be willing to supervise that year. Now, can you design an algorithm that finds an assignment to the advisors so that everybody's constraint is satisfied?
This can be formulated as a graph problem, right?
Yeah, very good. You can try to think of it in the graph world. That's excellent. Okay, so let me go to the 4th problem again. Okay, so good that you guys are thinking that direction. Okay, this is very nice. And you are going. The 4th problem is here. Okay, so this is another. So you have, say, n important locations in a city, and the telephone companies wants to upgrade its infrastructure, say maybe from 4G to 5G. Okay, and they want to do it in such a way that they want to upgrade the least number of infrastructure. Okay. And the idea is that if any location is within 1 kilometer from any tower that has been improved, then it is good enough. Now, of course, the company wants to minimize the number of towers they have to upgrade. So can you find which one?
It's like an MST problem.
This is not an MST problem.
Oh, okay.
This is not, but it is not an MST problem. No.
Okay.
Think about it. But it is. You can write it as a graph, but not as an MST problem. No.
Sure, sir. Okay.
So is it more like a vertex cover or something like that?
It is something similar to that. Yeah. Okay. So there is another one here. So I'm giving you another problem. Okay. Now, so there are various meetings are there. Okay. So there are 6 meetings are there, and each of them has a start time and end time. and the HR is supposed to say book or reserve as many rooms as possible, or as little rooms as possible, so that they can accommodate all of them, all the meetings. So how many minimum number of rooms do you need?
So it's like finding the chromatic number of the intersection hub, right?
Very good, very good, very good, excellent.
And
Yeah.
can't we do this using this topological sort kind of things? I may be wrong, I guess.
Yeah, try it out. Topological sort is a good, but since there are 2 points, this is not very easy to do it. I mean, it is not possible to do it actually in the topological sort. Yeah, think about it. But yeah, I must say this problem every year ISI Dean Service has to solve. When they have to find out how to have classes to schedule various parallel classes and all, how many classes do you need and so on. So anyways, good. So I'm very happy that you guys are all thinking in the right direction and thinking in various things. So I have given you 5 completely different looking problems to some level. How do you solve it? So, one approach that many of you have already figured out is what is called the linear programming. Now, you have not seen linear programming yet. Is that correct? As a subject,
We have seen linear programming.
you have seen
Yes. In high school days, actually.
in high school days.
Yeah, sir, I mean, the very basics with 2 variables at most.
I mean, you have done solving of various. Okay, fine, maybe. I mean, solving of what is that called? Multi-equation.
Inequalities.
Multi-equation inequalities also is there in high school days.
Yes, sir. I mean, like 3x plus 4y less than equal to say 9, and
Okay.
there are some 2 more equations. I mean, inequalities like that. So.
Okay.
So
So
just
we have just learned to solve that in using graphs. I mean, we plotted the
Oh, okay,
line.
right. You plotted the right things, then, right? Okay.
Yeah, and we get a convex region, and just we are told that the optimization happens at one of the vertices, so we have to check all the vertices and just that.
Right. Okay, good. So yeah, I'm in a bit of a not in touch with the high schools nowadays. So yeah, but okay, good that you guys remember. So, but it's exactly what you guys are telling. Okay, so you basically want to maximize a equation, which is a linear equation, linear expression rather, under the conditions that you have certain set of inequalities are satisfied. Okay, and this is all that we have to do. Okay, so this is what is linear programming is. The linear, because it's all of them, this one or this statement, so all are linear. You can write them. You can write everything as this whole thing can be written in a general setting using matrices and dot products with vectors and so on. Is that clear?
yes.
Yeah. Okay, so this is like, so there is a matrix A. So what we kind of, yeah, I'll let you guys think about it. How can you write a general thing using in the linear language, linear algebra framework? So okay, and in all of this thing, we are kind of assuming that X, Y, Z are reals. Right, so they are like, as you told that you drew the graph and plotted it, right? And there you kind of assume that X, Y, Z are real numbers. Now, this is what is LP, and this is a very, very important tool to solving various problems. So in fact, there are some nice packages in R and all those things that you can do. And say here, for example, I mean, this is what was there for forgot. So forget this law. Yeah. So this is something that I'll not go into details here. In your master's level, I think you will have this course on optimization, and you will see that linear programming is actually solvable in polynomial time. in polynomial time, so given an input which is the set of all equations or inequalities, and the expression that you want to maximize or minimize, whatever. When the variables are reals, then this problem can be solved in polynomial time. Okay, I am not going into it. It requires some amount of the algorithms are pretty involved. Let's put it this way, because the main idea is that this set of all equations gives you a polytope in the so if there's a k variables in r to the power k, and the problem is that it is fine exactly what you guys told, that the maximum or minimum will be attained at a vertex. The problem is that the number of vertices in a polytope might be exponential. So if you are just trying to find out all the possible vertices, then that's not good enough. So you have to come up with a better way of finding out a vertex which is which will try to achieve that thing. So there are particularly two standard ways of solving it, the interior point method and the ellipsoid method, which are known to be polynomial time, and I will not go into it. You will do it in your course when it comes. But for us, I am not interested in how LP is solved. Let's take it for granted that LP has a very quick algorithm. Okay, somebody has given me a machine or software that can solve LP. Using that, what can I do? And this is exactly what a person is expected to do using in, say, the industry, or when they're trying to apply apply algorithmic techniques in various other stuffs. Okay, the trick is in modeling the problems in the LP. So for example, you remember this transportation problem, right? So how will you do it? So one way is just to say that, okay, I have this okay, so here I have used it in a slightly smaller one. So you have this, say, 3 cargo and 2 wagons. So that means 3 into 2, 6. So there are 6 possible quantities or variables that you put in. Okay, so the x1, y1, x2, y2, and x3, y3. And once you have that, you can say, okay, so for C1, the cargo C1, x1 goes to wagon 1, y1 goes to wagon 2, and so on. And now all you have to do is write down the condition that neither of the wagons are over-sitting in the weight or in the space, and you want to maximize the cost. So which is basically maximize the cost under the conditions that the weights are all lower. So basically, okay, so you have another condition, right? That x1 plus x2, which is the total amount of cargo used, that itself should not be more than the total tonnage that is there available, right? And you have to put in this equation, which is the total weight going into each of the wagons, and you have the total volume, and you have this, all of them has to be greater than 0. That's it, right?
Yes.
Yeah. So like, I'm pretty sure you guys are all very comfortable with these things. Okay, but the crucial thing here is that we are not going to even think about how to solve LP. I just know that an LP has a solution, and my work is to just reduce this problem into an LP instance. Okay, we can do this similar. So this is this thing, and we have, with this condition, we will be able to solve it in polynomial time. Now let's go to the next equation. next problem that was there. Now this problem, how will you do it? I think one of you had already kind of pointed out what we can do. Right? So we can use the indicator variables. That whether I am going to invest in the Cricket World Cup or not, and so on. So I will think of this x1, x2, x3 to x5 as 0, 1 variable indicating whether I am investing it on the Cricket World Cup or not. And now we have some certain set of conditions, right? The cost has to be less than 6. The total number of people required must be less than 10, and the this we have to maximize the expected value. The variables are taking just 0 and 1 value, right? So you just write this, maximize something under the conditions, under these two conditions, right? So if we throw away the problem and just look at the kind of LP formulation, we have this.
Sir,
Yeah.
If we remove one of the conditions, doesn't this become a knapsack problem?
Yeah, knapsack is a special kind of that, no doubt about that.
So, okay.
Yeah. So knapsack is, these are very much similar to the knapsack results. Yeah.
So this doesn't have a polynomial time solution.
Yeah. So that's a good point. So this is a LP kind of a formulation, but the main trick is here. Okay, but main issue is here. That earlier we had this whole thing of these variables, if you remember in this previous one, where in the reals. That is what is linear programming. Okay, but when the values are not reals but integers, this is no longer a linear programming. We call this one as an integer linear programming, ILP. So these are called ILP, or integer linear programs. So it turns out that LP is in P. I kind of told you, I did not prove it to you. But what about ILP?
It's in NP.
ILP is in NP. Right? Okay, if somebody comes up with a solution, it's easy to convince me that that solution is correct, right? But I don't know how to prove that ILP is in P.
Sorry, sir. Could you please repeat what you just said?
I don't know how to prove ILP is in P. I don't have an algorithm for that. Okay, so ILP is in NP but not in P. So this is the main issue with this problem. So I have reduced it to some other problem, but that problem is not in P. Now I will leave you guys with the other two problems that are there. Maybe something is there. Yeah, so there are some things. So I will leave you guys with the other two problems, or other three problems. Yeah, where it's gone. Okay. And how to solve the other three problems. And what you will realize is that, okay, what we are able to do is that we will be able to solve the other three problems or reduce the other three problems into ILP, not necessarily to LP. Now I'm using this word reduction. Okay, and this is where I have to be a bit careful here. So now I will just try to think of it. Okay, so I have said two problems, L1 and L2, the languages. So these are decision problems. when can I use? So I want to check X is in L1. And your friend has given you a software to solve L2. How can you use L2 to solve L1?
Sir, could you please repeat?
So I have two problems, okay, L1 and L2. Okay, somehow your friend has given you a software to solve L2. How can you, but you have to solve L1, means you have to answer if X is in L1 or not. How will you be able to solve it here using L2?
We create a function so that.
So yes, sir, we can create witness.
It gives one, so that if in L2 also it gives one.
So you want to create a function witness. I think you guys are kind of come up in the correct genre, but exactly. So mainly that you have an input, right? I have, so remember that what was the thing that we were doing? We had this problem. The problems are talking about something completely different, right? We are trying to solve it. Instead, we wrote it as an LP or as an ILP instance. So idea is that means if I want to solve this, what do I have to solve? Okay, I have to solve this question, right? So I have to say that for all X, there exists an, okay, so maybe I should not write it here. Okay, so let me put it this way. So there exists a reduction, an algorithm R. Okay, what does this R do? So R is from say 0, 1 to the star to 0, 1 to the star. What it does, such that, okay, if I give you X, okay, I can put R and I get a new value, R of X. I converted it. And the idea is that L is in L1 if and only if R of X is in L2. If I can create such an R, what happens? I will be able to use a software of L2 to solve L1.
Right.
Correct?
Yes.
So in some sense, I have reduced L1 to L2. Okay. Now, okay, so this is what we call, this is the definition. This is called reduction. So this means that L1 is reduced to L2 and we write it as L1 is less than or equal to L2. Because L2 is harder, meaning because if I can solve L2, I can solve L1. Okay. Right? Now, of course, there is another issue here. If this R also takes some time, right? R also has some computational time. What happens? R is too costly an affair. Then that is no good. I mean, your friend has given you a software, but to produce that reduction, you have to take X and you are putting that R of X, but that takes hell lot of time. That's not good, right? So if I have to write it here again, so if I have R, okay, so I have an algorithm R which runs in polytime. R is a polytime algorithm, meaning, okay, and X is in L if and only if L1, if and only if R of X is in L2, okay, then we write it as that L1, we kind of put a P to kind of denote that it's the polytime reduction. L1 is reduced to L2, being a polytime reduction. So in other words, it means that if this happens, and if somehow L2 has a polytime algorithm, L1 also has a polytime algorithm. Because you will use that R to reduce, change it, and put in and solve it in L2. Is this concept clear?
Yes, sir.
Okay. It seems very trivial for you guys, possibly, because once you have this one, but we need to kind of formalize this thing importantly. Okay. Now let's come back to this NP and co-NP thing. NP and P. Okay, so here is a theorem. This theorem is I will not prove this theorem, unfortunately enough. So this theorem is by Cook and Levin. This is from 1971, I think, or 70. I think. There exists a problem in NP such that, so there's a problem. So there's a problem, and they had called this problem SAT. Okay, I will put it this way, such that for all L in NP, L polytime reduces to SAT. What does it mean? Just try to understand it.
So we can reduce SAT to L.
I mean, yeah, we can reduce. No, we can reduce L to SAT. Or I mean, whatever.
I had one question that suppose we are writing that L1 is this less than equal to L2. Suppose.
Right.
So I mean, if L1 can be reduced to L2 in polytime,
Right.
L2 can also be reduced to L1 in polytime, right? Shouldn't it be?
Should it be? Think about it.
I mean, since they're equivalent, therefore.
I'm not telling you it's equivalent. I'm just saying that L1 is reduced to L2. That's all. So this definition doesn't require L2 is reduced to L1. Because the R is not a one-to-one correspondence.
Sorry, sir. This R is not.
Not a one-to. I mean, it's not a bijection, right?
Sir, since this is an if and only if relation, it should not be bijective. I mean,
No. I mean, what is this statement saying? See, R of X is not the range of R is not the whole thing. Right? I mean, R is from 0, 1 to the star to 0, 1 to the star, but that doesn't mean that every point in X has a pre-image. Every point in the range has a pre-image.
okay, sir. Okay.
Right?
Sir, so this L1 less than equal to L2 means that L1 can be reduced to L2 or the other.
Yeah. So L1 is reduced to L2. In other words, you can. Now I myself get forget about this.
So if L2 is easy to solve, then definitely L1 will be easy.
Exactly, that's the main idea. Okay.
Something like that, right?
Yes. So L2 is harder than L1 in some sense. If L2 can be solved, L1 can be solved. L2 can be solved.
Okay.
Okay. So that's how you should think about it. I myself forget about this English statement of which reduces to what.
Then
The main.
L2 can be reduced to L1, right?
Okay, let's live with that. Okay, so L2 can be reduced to L1. Okay, the inequality wise is fine because the L1 is easier than L2. Okay. Just I mean I can just check in the internet what is the exact terminology which this is to what.
Sir, it should be L1 can be reduced to L2 because like we were seeing in our examples, we were reducing them to a standard problem which was harder, right? We were reducing them to an ILP, something like that.
Yeah, I think, yeah. So I think your whatever I told is right. So L1 is reduced to L2. Yeah. So this means that L1 reduces to L2. Okay, so you can use L1, L2 to solve L1. So you can take an instance of L1 and you can convert it to an instance of L2 and live with that and solve that. Okay. Is this fine?
Yes, sir.
Yes.
So this theorem that you have that I just wrote, this is one of the most amazing theorems in mathematics, actually speaking. Because now, what was it? If you had to prove P is equal to NP or P is not equal to NP, the point was that I have a P which is a set, right? And I have a NP which is another set. And I was asking, is this two sets same? Right? To prove the two sets are same, the way to prove it is that every element in NP goes to P.
Yes, sir.
Right? So that's very hard. How can you prove every element of NP goes to P?
So
What?
if we can show.
This
Yes.
theorem says that there exists a point here. Let's call that one SAT. That problem is the hardest problem among NP. So if that problem goes to P, then the whole NP goes to P. So if SAT is in NP, so is in P, then
P is equal to NP.
yeah, P equals to NP. And now if of course P is equal to NP, then SAT is of course equal to P, because SAT is in P. So this is if and only if. So this conjecture suddenly pushed this whole thing of concept of a hardest problem. Okay, so such a problem is called a NP complete problem.
The SAT.
The SAT is an NP complete problem. Okay, but now there are some more interesting things. What happens if you have another problem, say L, okay, and you prove that SAT is reduces to L? What does it mean?
So the R would be the bijection then.
No, not necessarily bijection. I am not saying that, but at least what we can say is
Here,
that
L is what?
L is some language, say ILP for that matter, say
L is in NP.
ILP.
That does it
So
belongs to
is
NP?
L also in NP?
Huh?
So L we are taking in NP, right?
NP, yeah.
So L must also be NP complete. then.
Yes, that means ILP or LP, whatever, for anything, okay? So I should write it as L, okay? L implies L is also NP complete. Why? Because see, any language, say L bar, or sorry, bar is not a good idea. So L1, this reduces to SAT, and SAT reduces to L, which means that L1 reduces to L. Like two step, and you can write it if you want. You can just put this compose these two functions of R1 and R2 or something. Okay. So here we are. So in fact, I can tell you this following thing. So I am not defining SAT for you guys. Okay. I am going to leave it to you to go back and check this whole thing. What is this SAT? It's called satisfiability. I am telling you to go and check what is this class of functions or what is this problem. Okay. Maybe if I have time later on in this course, I will kind of go back and try to talk about it a bit more. But this is a very important problem. But what happens is that this problem SAT is proved to be less than or equal to ILP. Okay, this is a theorem. Not only that, I also have a theorem that SAT is less than or equal to vertex cover. I also have a theorem that SAT is less than or equal to knapsack.
Yeah.
So all of these problems, they are called the NP complete problems. And note that NP complete problems, they are all equivalent to each other because they are the hardest in the class, right? So one is taking down the other one. So if I can prove vertex cover is in P, then that means SAT is in P, which means ILP is in P, right? So,
So these say NP complete is it's collection of problems which are essentially SAT, right?
basically, yes. So you
Like
can
if
think
we are
of
able to,
this is a set of all languages such that SAT reduces to L.
so if we have solved any of one of these problems, then we have proved that P equal to NP.
Exactly.
I mean,
Okay.
if we have found the algorithm in polynomial time.
If you find an algorithm in polynomial time for any of these languages, you are done.
These NP complete problems are all reducible to each other, right?
They are all reducible to each other. Okay.
We reduce
Sir, and
reduce SAT to that.
Yeah. Yes. All of them reduces there. Yeah.
sir, and so this might be a silly question that so what are the consequences of P is equal to NP? So suppose P is equal to NP, then I mean, why do we care?
Okay. Why do we care? There's a lot of things. First of all, there's a philosophical thing, right? I want to know how hard is it? Can every problem be solved and all? Okay.
Sir, but I mean,
And otherwise, also there are many things. Okay, including the factorization that I talked about, and all. Okay. So many of them are in NP but not in P.
Sir, it does not help us in finding any algorithm, right?
If P is equal to NP, then it will help us. If P is equal to NP, that means there is an algorithm, polytime algorithm to solve SAT, the polytime algorithm to solve ILP. Right?
So far, so we have not been able to find out any problem which is in NP but not in P.
We have not been able to prove it because else we would have done P is not equal to NP.
Right, sir, right.
Yeah. So if you draw this class here, so I have this NP, this is P, and there is a class for here, we can call it as NP complete or NPC. So all the problems here are equally hard. Okay. So now, why is this important for us in the algorithms world, in the world of industry or anything? There are two ways of doing this whole thing. Okay, there's two ways of seeing this whole thing. So if I give you a problem L and I will solve this problem. So I have some other problem, say I have defined out a problem and I ask you design an algorithm for L. How will you go about it? Hello.
Yes.
Say, what's the structure of the problem?
I'm not telling you the structure of the problem, but I'm just trying to say what all the steps that you can do.
We check if it's in NP.
Yeah, the first of all, you can check that, okay, is L in NP? Okay, so maybe you can just check is L in P by is in L in P using simple algorithmic techniques. Of course, that makes complete sense. Okay, so use DP, dynamic programming, use greedy, you could do something, you do something and check whether it solves in polynomial time. If you can, we are done. But if not, the next thing would be to check is L in NP. Now say if it is yes, then okay, so L is in NP. That means they can verify. Then the question is that, okay, why am I not being able to find a polytime algorithm for this L? Is it because I have not tried hard enough, or I have not been able to come up with the correct way of thinking? Or is there some other reasons for that? So the next thing that one tries always is that is L in NP complete? How do you prove L to be NP complete?
We reduce it to SAT.
You can the opposite direction, yeah. You have to reduce SAT to that language, or you can reduce anything to that language. ILP to L, done. Or vertex covered to L, then done. Or basically for any, find a language, or I'm using the language, finding a problem, say L prime, that is known to be NP complete, and prove L prime is, you can reduce L prime to L. And if you can do it, you're done. What you are done? You're not done, but you can say now, convince. Say you're in your industry, you have a boss who comes and says that, oh, why don't you not come up with a clever algorithm for him? This shows that, okay, see, I have not been able to come up with a clever algorithm for L because the language is NP complete. So if I could have come up with a polytime algorithm, then I would have proved P is equal to NP, something that nobody has been able to prove till now. Right?
Yes.
Yeah. So, but that's not the end of it also. Okay. So once you have this thing, then what do you do? The next thing that you can do is that you know that L is in NP, right? What you can do is that you can reduce L to SAT. And since SAT is one of the most popular, or you can reduce to ILP, right? Now, of course, we don't have polytime algorithm for SAT or ILP, but we have, see, these are the kind of central hard problems. Okay, so people have been working on it. So just because we don't have a polytime algorithm for ILP doesn't mean that people are just sitting there. People have come up with lots and lots of what is called as heuristic algorithms. For ILP or for SAT. So it's like we don't know how to solve it exactly, but there are algorithms for that are not, we can talk about it a bit more in the next class or some other later classes. So these algorithms are not necessarily in the worst case polytime, but they can possibly polytime for many cases. For many inputs, it quickly outputs the correct answer. Okay. So it's not guaranteed to run in polytime, but if whatever it outputs quickly, and it will give you the correct answer. But maybe for some inputs, it can take ages. So these are called the ILP solvers or SAT solvers and so on. So in big companies like Google and IBM and all those things, these solvers coming up with a very clever algorithm that somehow manages to solve that. Now, these are like the main ideas of that. So it's not, I should say, they are not, should write it very clearly, they are not polytime algorithms. Polytime in worst case. But what you can somehow say is that, so what was the polytime means? That for every input, it has to output in the correct answer in polynomial time. But maybe I am happy with answers that are on average correct, meaning or average quick, meaning maybe there are average time in polytime, or we can say that for natural inputs, they run in polytime. Now, what does natural means? Natural means inputs that are occurring in practice. So these are all, none of them are, the proof of correctness is fine, but they don't have a guarantee that they will run quickly. But for many instances, runs quickly. And these are what we call as the heuristic algorithm. So that is the other thing that you can guys want to do. The next thing that happens, and this happens in the world of theory rather than in the world of practice, the SAT solvers and all is in the world of practice, is that, okay, I know that L is in NP complete. So I don't expect to find a algorithm that solves it in polynomial time. But can we solve this language or problem L approximately? Or using randomization? So a purely deterministic algorithm will not be able to solve it in polynomial time. But can we come up to something? So for example, in the case of ILP, okay, maybe I don't know how to find out the exact maximum quantity, but can I come up to something which is close to the maximum? Can I answer whether, can I output the some value which is almost as good as the maximum? So these are the areas of things that happens, okay? So these are what gives rise to what is called as the approximation algorithms. Randomized algorithms. There is also parameterized algorithms. There is smooth complexity algorithms. And so on and so forth. There's a huge number of this, not huge number, but there's quite a few of this kind of techniques. Now, in the first course of algorithms, we will not be able to go into all of that, or none of that, in fact. Okay, but I am pointing out that this all starts from understanding what is the complexity of L. Is L in NP and is L NP complete? Okay. Any questions?
Sure. So if we're not able to show that it is, if it's like something in NP but not in NP complete, then we just have to try to get it in P time.
Yeah, so that's what is the belief right now. Let's put it this way. Okay, although I mean it might happen that it is in NP but not in NP complete. There are theoretical reasons why it can be. So there are theoretical ways that there can be problems here, but those problems we don't believe to be actually very natural. So if you start with a natural problem, it will be naturally I mean, this is how it kind of falls. Either it goes into polynomial time or it is NP complete.
Sir, what is the belief that you said?
That yeah, I don't want to go into this, going into too much into this complexity classes or something. So there is a theorem. Now this theorem is something you don't have to know, but so there exists language. So sorry, maybe I should write it very carefully. If P not equal to NP, then there exists a language L in NP minus P minus NP complete. NP minus P intersection. Okay, so there exists such a language here. But this languages that the theorem guarantees is called a Ladner's theorem. So Ladner's theorem. So what this problem guarantees that there exists a language, there exists a problem, but that problem is a very artificially created problem. So we don't believe that there are problems in this class, or most of the natural language in the class should be either here or here. Okay, so very unlikely that you will actually come across a problem which is actually here.
It's not so we cannot find any, right? If we are able to find,
I mean, no, if you cannot be able to find, of course, if you can find, if you can prove that, oh, this is a problem that is not in NP complete or in P, then you have proved P is not equal to NP.
Yeah,
not,
yes, that's
yeah. So, but see that if you have a problem, then it should be almost always be either be NP complete or in P. That's basically what I wanted to say.
Yeah. Sir, so far in this course, we have seen some problems. So
yeah.
And we have been told that to find out an algorithm to solve this problem.
So
like
all
this.
of them are in P.
Yes, sir. So how do we actually prove that? So suppose we do not know that, I mean, suppose we could not come up with some algorithm, then
Yes.
is there a way to prove that this problem belongs to P or NP for sure?
So that it is a problem that we face regularly. Okay. So we sometimes, so the standard thing is that we try to solve it in somehow. Okay. Not necessarily quadratic or cubic, but somehow can you solve it? And sometimes we are unable to do it. Okay. But once we are unable to do it, then usually we go and try to prove whether something is NP complete. So there's a huge compendium of class problems that has been proved to be NP complete. And we try to see if there is a problem which is similar to this problem, which is known to be NP complete, and then reduce that problem to that new problem that we have. Okay. So in fact, that is exactly what we will be doing in the next class or something like that. We will go over a few problems and try to prove them NP complete. How do you prove something is NP complete? Any other questions?
so. So
yeah.
So what are the NP complete problems that we should know that would be useful? I mean,
to start with, ILP and SAT. I have not told SAT is okay, but SAT is a very standard thing. So you can take a look at this thing. I mean, I might talk about it a bit later in the course, but ILP is a very important NP complete problems. Vortex covered is. Then there are a lot of these things. The Hamiltonian path is. Chromatic number of a graph is. Subset sum is. So almost many of these problems that you have seen are NP complete problems. So we will see a series of the problems that are NP complete. If you search in the internet and search for a compendium of NP complete problems, you will find a huge collection of NP complete problems written there. Okay. So I must say that one thing that you should have asked is, how do you prove this theorem? This theorem is quite an. How do you prove that any problem in NP can be solved to some particular problem? This is a theorem. It's not a kind of a dialogue or a fact that I'm saying. It's a mathematically proven theorem.
So maybe the formulation of SAT was such that it contains that property, and then we just show that it was actually NP.
So if we are able to find
Yeah.
a reduction, if we are able to find a reduction, proper reduction for any problem in NP, and we are able to get SAT, then we are.
Okay, so I mean, I think, yeah, I mean, it was a kind of a trick question because I'm not introduced to certain things. A certain thing is that what does any problem in NP mean? Okay, so I told you that any problem in NP means there exists a polynomial and all those things, and there is an algorithm that works, right? The important thing that I left out there in the definition of NP is what is an algorithm.
What is an algorithm?
Yes, mathematically can define an algorithm. And in fact, if you do that, if you manage to define algorithm properly, define a polytime algorithm properly, then you will have this answer. Okay. So I kind of told you guys to go and read it, but I did not push it for it. So I'm also doing it here. To define an algorithm, you have to look at Turing machines. Once you define the class of NP using Turing machines, then we will be able to reduce, we will prove this theorem. So what I can do is that I don't want to really put Turing machine in this course because this will become a bit too much of a hassle for many of the other people, and that's not good. But in case you guys are interested, I can either myself take or ask the TS to take a particular extra class that will be not part of this course, if whoever wants it, to define Turing machine, define the class NP using Turing machines, and then prove this theorem. But yes, SAT is actually, I can also define this concept of SAT. So the SAT problem is actually not very hard to define, okay? So SAT problem is that it is a formula, okay? So I have some variables. Okay, so say let's call this one x1, x2 till xn. So they are taking values true or false. Or if you want to think of it, is they are taking values 1 or 0. And the Boolean function, you have this conjunctives, right? Say or. When is or? When is x1 or x2 is true, if and only if
Both of them are true. Sorry. At least.
At least. Okay, if x1 is true or x2 is true, it is not exclusive or, right? Similarly, I can define and. Similarly, I can define, say, x1 implies x2, and so on and so forth, right? Now I can write a formula using that, right? So x1, x1 or x2 or x3, and I also can define a not of x1, right? Not of x1 or x4 or x5 or not of x6 and something. I can write it like that, right? SAT is asking that I will give an input. What is the input? This is called a Boolean formula. The input is the Boolean formula. And the output. So for example, here, like say here, I can define it like this, right? I can define x1 or x2 and not of x1 or not of x2 or something like that. Now I can say, is this formula satisfiable? What does it mean by that? It means that is there a way of putting values to these variables? So I can put, oh, let's put x1 equals to true. Okay. If x1 equals to true, then this is satisfied. This clause is satisfied. This is a clause, but this is and. So this part is true. Therefore, it's an OR. What about this part? Okay, this part is not necessarily right because x1 is so false. It is becomes. So what happens if I put x4 equals to true? If I put x4 equals to true, this is satisfied. Of course, this is also satisfied true because x2 is true. No, x1 is true. But what about this one? Okay, I have to put x2 equals to. If I put x2 equals to false, then this is true, and then I'll be done. So that means output is 1. So if there exists an assignment to the variables that make the formula true. That's it. Okay. So the problem of SAT is a very simple definition of Boolean formula. Is it satisfiable or not?
There are all algorithms Boolean formulas.
All algorithms, what?
Are all algorithms Boolean formulas?
No, all algorithms are not Boolean formulas. Why is all algorithms Boolean formulas? They're not.
Can we represent all problems as a Boolean formula?
No, you cannot. I mean, you can write all formulas as a Boolean formula, that's true, but it can be of a massively large size.
Right.
Size can explode. Okay. So this is this problem of SAT. You have seen the problem of ILP, you have seen the problem of water cover. All of them are NP complete. Okay. So if you guys are interested, I can try to define Turing machines in one of the extra classes and prove you this statement. Or if you guys are interested, you can read it for yourself. For example, I know that the Corman, Lisserson and Rivest book, CLRS, that one has a proper proof of this theorem. This is one of the most celebrated theorems in whole of mathematics.
These things are purely mathematical, right? So apparently there is no computer science in these things. So these are computer science problems maybe, but the formulations are mathematical, right?
I mean, what do you mean computer science?
Sorry, sir?
What do you mean by computer science?
Yeah, that's a difficult problem, to be honest.
Yeah, I mean, these are mathematics. I mean, we have been taking this class for some time. I mean, which part of this algorithms course did you find to be not mathematical?
Right. Sure. Yes.
At the best, you can say it is discrete. Yes, we talk about discrete stuffs. That's true. Not necessarily going into the continuous domain that part. Okay. So, I mean, I think we are really hovering at the edge of algorithms and complexity theory. So I will not be going any further than this today. I have defined you NP complete problems. What is NP complete and how NP complete problems can be used. Okay, this was more of a very important thing. In the next class, I will be going over some of the reductions, how one problem can be reduced to the other and so on. Okay, to show how you prove some problem is NP complete. But from your understanding of algorithms, I think this class is very important, this particular lecture, because this will kind of tell you that, I mean, when you go to in a real life problem or a problem in research also, you get a problem and you are hardly ever, somebody is going to tell you that, oh, go and find out use sorting to solve this problem. Those are simple ones. Most of the time, you face a new problem and you have to kind of understand whether you can come up with an efficient algorithm or not. And you do face NP complete problems and so on. Okay, so in terms of the algorithms understanding, this is very important. The concept of NP completeness and how to prove something is NP complete. And the whole, more importantly, the whole concept of how you can reduce one to the other. So we have seen some reductions. And I will let you guys to go back and think of, try to prove the other three problems that I wrote. How can you answer them using, yeah, I mean, how can we reduce it to say ILP or something? It's fine. Any questions, any doubts, queries, anything?
Sir, can you please suggest some resource where all these things are there? I mean, in a compact manner. Like,
I mean, any book will have it. Whatever I did today is still in the algorithms book. Okay, take Corman's book or any of the books will have this thing subject. There is a chapter on NP completeness, NP, NP completeness. Any algorithms will have that.
okay, sir.
Okay, so I have not got anything beyond what is done in algorithms. Okay, I'm just saying that this subject is unfortunately very close to complexity. So complexity theory, we just go into a bit more involved stuff after that. We talk about, I mean, this is where the start of complexity theory happens. Any book will have whatever we have done till now. Okay, any questions? So if not, let's stop here today. And we will meet on Tuesday again, right?
Yes, sir.
Thank you, sir.
Thank you, sir.